Okay, so from our equations here, right, we got ML, which is our angular momentum. And, well, our angular momentum quantum number. Sorry. That is, L is our angular. Okay. So because the angular momentum, right, we saw previously that our angular momentum, our J, was proportional to our m sub L, right? Because this is quantized, what that means is when we're looking at things down at the atomic level, one of the weird things is they can only spin in certain directions, right? So their arrangement or how that angular momentum vector is pointed is quantized. It can't spin in any particular arrangement. So a way of thinking about, and this is a much better drawn figure in your book. I think it's, I don't have the number. All right, so if we have a spinning thing going around this direction, no, spinning the other way, right? Because so something spinning coming around this way would have a vector going this way. So this is when ML is equal to 0. When ML is equal to -1, we point it down like this. And so your spin would be going around that direction. ML equal to 2, like this. These are typically unit vectors, and people with better art skills can draw it such that they look that way. The interesting thing about this is it only has particular angular ways that it can spin. Right, it can't spin where it's rotating, or the axes of rotation is limited to the directions that it can occupy in space, which is counter to what you would think from classical physics. Right, you could take a spinning top and you can spin it, and you can orient it however you want. But when we're talking about things on the quantum level, you can either have it horizontal or at an angle that corresponds to 1ml, or ml equal 1, ml equal 2, right? There's only specific values that it can be. This is where the concept of our spin quantum number comes into play, right? So that is your m sub s value. So back in 1921, Otto Stern and Walther Gerlach, or however you properly say that in German, tested the idea of spatial quantization. So what this here is saying is that where something can rotate in space is quantized. So you have a spatial rotation component. It can't be in just any angle that it's rotating. It's very set angles. So they tested the idea of spatial quantization. This also comes about from the Bohr model of the atom, where you had planetary motion, things going in a ring, and then you have the electron, which is interacting in a magnetic field. Theoretically, if you have a charge, it's spinning, and so it should have like a magnetic dipole, right? So back when Bohr model was still something that people used, these two German scientists decided that they were going to test it. So they selected the silver atom. The reason that it's silver is you want something with a single electron that has spin. Right? If they're spin coupled, then those magnetic dipoles are going to cancel each other out. So you want something with a single unpaired electron. You wouldn't want to use any of the alkali metals because they are not happy in air, right? And so, if you remember your Aufbau principle, Hund's rule, and all that sort of stuff, filling this up by fully filling the d orbital, it becomes more stable. And so normally what you would expect this to be, silver would be 5s2, 4d9, but by promoting, yeah, we don't have a periodic table in this room. So by promoting an electron from the 5s to the 4d, you close the shell, it becomes more stable, and then you have a single electron in the 5s. So your electronic arrangement in your valence shell ends up looking like that. This is the key part. You have an electron spin up. The reason you select silver is because that's the property of it, right? It has a single spin up electron. It is paramagnetic, right? It interacts with a magnetic field. The other reason you use silver is we can actually get it into the gas phase. You have to heat it like you wouldn't believe, but you can get silver to evaporate. So you heat it up, silver evaporates, and then you confine it to a beam, and then, so this part one is where you have your silver being evaporated, push it out in a beam, have a couple pinholes to confine the beam to a nice narrow stream, right? So that's what's occurring here. At step two, that's your beam of silver. You run it through two magnetic, you run it through a magnet. The thing about this particular magnet is it's not uniform in nature, right? And the reason why you don't want it to be uniform in nature is, let's say you have your magnetic field here. This is your plus end, this is your minus end, right? And say that's your plus, that's your minus end of your silver atom. So you got your, I guess an s orbital, but s isn't sure. So you got a plus end and a minus end. What it's going to happen is, as it's flying through, it's going to orient to the field. And so after a bit of time, what you should see is sort of your minus end here, your plus end down there, oriented to the field. It would then stay in place, or it might spread out a little bit. So via classical physics, what you should see on the other end of your magnetic field, well, if it's a uniform field, you should see a dot, because the force going up and going down is the same. If instead, what we do is we have the bottom field be a much wider plate and the top field being a much narrower plate, then all the plus charge on the top will be confined to a smaller area, in which case the force going towards it is going to be greater. So right now, the force going up balances out the force going down. The force pulling it to the negative plate balances out the force to the positive plate. If, however, we shave the top plate, so we had 5 pluses, 5 minuses, the positive is now confined to a smaller space, and so the force vectors are going to be going this way, right? Which means that instead of just orienting, it'll start moving towards this plate if you have a particular spin or the magnet pointed in a particular direction. So what you would see is it comes out and it would arc up. And so you should see a sphere like that if the magnet can orient in any direction going in, right? So if we don't have quantized angular momentum, right, then it can come in at any particular angle, in which case if it comes in at one angle, it might end up here, or here, or here, and so you'd end up with a whole bunch occupying a lot of different space. What we end up seeing is bright spot there, nothing in between. Right, so for an electron, it can either be spin up or spin down. Right, there's two different ways that it can have spin. The tricky part is, in terms of terminology, the electron itself doesn't actually spin, it's said to have spin. It's this weird notion of if you can't have, the electron itself can't be spinning, because then it would be throwing off the magnetic field as opposed to interacting with the magnetic field.
So the electron's not spinning in the magnetic field?
Huh?
So the electron is not spinning in the magnetic field, it's just like going, like...
It's said to have, no, so it does, so the whole concept of the electron is that it spins around in a circle like planetary rotation, right? That would cause a magnetic field, and so it interacts with a magnet, but that also causes a bunch of other problems that would cause serious issues. So because the electrons themselves interact with magnetic field, we say that it has behavior as though it had spin, but it doesn't have all these other problems with an electron having spin.
So it does spin, but it doesn't.
Yes. So we say that it has spin as opposed to it spinning. So it has the behavior of something that spins, but it doesn't have all the behavior of something that spins. So when we're talking about an electron is spin up, we don't say that it is spinning clockwise. We say that it has spin in the up direction or spin in the down direction. It's not that it is itself spinning. Yeah, electrons don't spin. They have spin. So it's a property that mimics what in the real world, in macroscopic terms, we would see as a charge that spins.
But if it were to actually spin, then it would have more complications.
Yes.
So when you say plus or top spin or up spin, down spin, what does that mean? Just electron has
It's essentially like a bar magnet pointed up or a bar magnet pointed down. So it will either interact positively with the magnetic field or negatively with the magnetic field. So when it interacts positively with the magnetic field, we get this spot. When it is oriented such that it interacts negatively, it's this.
That means when it goes top, it has top spin on it.
Yes, it has positive spin.
It has positive spin, so when you, also it depends on what your magnet setup is. If it's like negative on top, yeah.
Yeah. Okay, so that's what we mean by electron spin, is that how it's interacting in the magnetic field, not that the electron is actually spinning. It's physicists attempt to come up with terms that are related to everyday life on things that have no relation to everyday life. Right? Things that happen on the quantum scale don't behave the way we expect them to. For example, the quantization of the angular momentum. If you take a top and you try to spin it, you can rotate it 360 degrees and without a problem. On the quantum scale, you can't. There's only certain orientations, and if it's an electron, it's either up or it's down. You can't have an electron off to the side.
So in that, right?
Mm-hmm.
Electrons moving this, up spin this way, all the way around. respect to the central nucleus.
No, they don't rotate around.
What do you mean?
Electrons don't have nucleuses.
Huh?
No, like in an atom, we have nucleus and electrons.
Uh-huh.
Electrons orbit the nucleus, no?
No,
Yes,
that's,
they do.
no, that's the Bohr model. The Bohr model died in like 19,
The entire
28.
rotation of the nucleus is electron going around the nucleus. So what does the electron do in the nucleus? Just stay there?
no, so the problem with electron rotating around a nucleus, right, is if you have an electron as being a dot, you know, the standard Bohr model, if it's a dot and it's rotating around, then it has position and it has momentum that you know what it is. So if we know what the position and the momentum is, then we've just violated Heisenberg's uncertainty principle.
Well, we don't know the position, it's just like somewhere in that thing.
If it exists as a particle, then it has a defined position. And if it's rotating around in a ring as a defined particle, then it has momentum that we can know.
Okay. An atom is made up of nucleus and electrons, right?
Yes,
What are electrons doing?
they are occupying space.
So they can't be stationary because if they're stationary, they're at zero temperature.
Correct,
So they're not just staying,
correct.
they're moving.
Sort of, yes.
So if they're moving, they have to be going around it. They're just moving back and forth like some random orientation and anyhow they want.
Mhm.
It's time to change behaviors.
Which makes sense.
We are gonna be getting into that in the next chapter.
It makes sense. What do you
Yeah, it makes sense.
Oh, does it
It's
make
just-
sense?
It's just like an electric cloud.
That's
Then you
exactly
have
what
a-
it is.
Then you have
That's-
density,
that's-
and you
that's-
have probability of where it's gonna be.
Yeah. This is not an electron cloud. This is an electron in one spot.
So it could be anywhere in that cloud whenever it wants.
Yeah,
But it doesn't follow a circular motion.
no.
This goes this.
Sort of, but no.
It doesn't even move, it just appears.
It's, so where it is in space is a mixture of a wave-like behavior and a particle-like behavior. It doesn't actually have a position in space until you measure it. In that case, you're.
Well, that's the also like Schrödinger had.
Yeah.
superposition.
Yep, that's the superposition. When you measure it, the superposition collapses to a point, and then you have the electron here. But you no longer have any wave-like behavior, so it doesn't really have any discernible momentum that you can find. It has momentum, but you can't figure out what it is because the momentum is stored in the wave information. And so you know its position, but you don't know where it's going.
Actually, that's still gonna be wrong in like 10 years. No, we thought that was wrong as well. This is revised against confusing your students.
Well, yeah, this is, quantum is confusing, and the people who came up with it were confused by it.
So are protons and neutrons stable in the nucleus? They're stationary, right? Like they're vibrating, they're stationary, they're staying in the center, right?
For the most part, yeah.
Why don't we take chemistry for that's not even true then? Like the whole chemistry curriculum is just basically learning this, and comes to quantum is like, nah, throw that all out.
So the reason why we teach you the stuff we do in general chemistry is to, depending on what scale or what you're looking at, to a good approximation, the Bohr model actually explains a lot. It doesn't explain everything. So you need to know when your model fails, so that you know when to use it and when not to use it, right? So if you're trying to talk about the lines of like a hydrogen spectra, Bohr model works perfectly fine. Problem is, helium, it doesn't work. Or if you're trying to do like HOMO-LUMO or different energy levels, it doesn't work.
So not only we can't even explain electrons' position or movement in one single atom, we can't really explain when they form bonds. Because what happens when you have like one atom goes close to another atom, they form a bond. What happens to electrons then?
The probability density cloud gets shared between the two atoms.
So electrons could be either in one atom or the second atom.
Yeah.
Yeah, it's like a bond, but it's like a part of, like, so like the nucleus.
It makes sense, but
and then
like,
it's
wait.
and then the electrons kind of float around.
Okay, the good news though, that's the end of chapter 7.
So much math.